All right. Excuse me. Good afternoon, everyone. So, if you're at home today, this is the short video that you'll be watching. We're going to talk about some pretty important stuff today. And when I say pretty important, I mean like stuff that will be with us for the rest of this entire class. So, it'll be pretty important. But first, before you do anything and before you actually watch this, please make sure to first, right, answer the FRQ that's on Google Classroom. I believe it's from 2017. I believe it is question 4. Now, what that actually means in terms of the scale of the FRQs on the AP Stats exam, number 4 is the second hardest question that you are expected to know exactly what to do. The reason why I say that, the very last question, number 6, is always called an investigative task, meaning that it's going to take what you know and then ask you to extend that knowledge to a new situation. So it's very difficult to prepare for those because they're different every single year. But of the first 5, those cover everything that we've done in class in a straightforward fashion. This is the second hardest one. So that should make you feel a little bit better just because this question isn't super difficult and it's something that we already know how to do, and it's the end of September. All right, so very first thing, go ahead and try that question out. Please submit your work, right? This will allow for me to give you some feedback and give you an idea of, based on the AP scoring guidelines, what score approximately do I think you would get, just so you know where you stand, what maybe you need to improve on, what are you doing well, where can you change your wording to make sure we're checking the right boxes. So very first thing, please go do that. So if you didn't do that already, pause the video and go do that. Now today, what we're going to talk about is the normal distribution. Now this is like the holy grail of statistics. It is one of the most important things that you'll see all year, right? Now, first question is, what is it, right? So the normal distribution is a probability function that describes how the values of a variable, a quantitative variable, that is, are distributed. Right? And so it has a few characteristics as well that are extremely important. Number 1, it is symmetric, it is unimodal, and it is bell-shaped. So if you've ever heard the term bell curve, like SAT scores are graded on a bell curve, or AP exams somewhat, right? That term comes from this normal distribution, right? And so the other idea here is that further from the mean, or further from the center, I don't know why my stylus just freaked out there. Further from the mean, there is less probability. So if I draw you here a basic picture, right? So here's my number line. A bell curve looks something like this. That is my best sketch of a bell curve, right? Now, some important aspects here, right in the middle here, this is your mu, or your x bar. Difference between those mu is if you have a population level, right? The population mean, for instance, if I took the mean SAT score for every single person who took the SAT, and I found the average of all of that. X bars if you have a sample, meaning if I just took a smaller group of, let's say, 100 people and computed their mean SAT score, right? And then we have data, all underneath here. Now, what's important is the area underneath, right? So let's say, right, from right here, if I shade this, right? So this is somewhat of a calculus concept, right? The area represents probability. So the area under the curve represents the probability that something is less than or equal to or greater than or equal to, depending on what side you are looking at. So that is very, very important to wrap that around your head. There's a table that I put up on Google Classroom, and it's called the Z table. So if you take a look at that, all of those corresponding numbers, right? Actually, let me see if I can pull that up for you here. Google Classroom is not working before. Oh, it is. Perfect. Right. There we go. So if I show you this here, if this loads, this Z table right here, if we take a look, notice how there's an arrow that points to probability. All of these numbers in this table represent probabilities of being less than or equal to a certain distance from the mean. Now we're going to talk about that in a second. You see all these numbers on the left-hand side, negative 1.6, negative 1.7. That will all make sense in a second, right? However, there are a couple of important properties because of this symmetry right here that come along with the normal curve. One of the most important is called the empirical rule. So, what that states, and I've seen many, many multiple choice questions about this, right? So this is a common multiple choice topic. Very common because you can do things very quickly. What it states is, right, within 1 sigma, in this case if you remember, sigma stands for standard deviation of your mean, you have 68% of your data. So plus or minus 1 standard deviation represents 68% of your data, right? Within 2 standard deviations of your mean, you have 95% of your data. And within 3 sigma, you have 99.7% of your data. So oftentimes, you'll see this rule referred to as the 68, 95, 99.7 rule. And I will use that as well in class to simplify wording a little bit. So to give you a graphical representation here, we draw a bell curve, right? One important thing too, right? The bell curve on this page doesn't look exactly like the bell curve on this page. As long as it is symmetric, unimodal, and bell-shaped, it's considered a normal distribution. This height in the middle here doesn't always have to be the same height. Some normal curves are flatter. Some normal curves are taller. A great example of this would actually be back in March and April when everyone was talking about flattening the curve in terms of coronavirus. They weren't talking about making it a non-normal distribution. They were talking about changing the type of normal distribution. Instead of having a really tall peak in a very short amount of time, we wanted to flatten that curve out, make it slightly flatter, make the peak shorter, right? But spread it out over a longer period of time, right? So now to illustrate our 68, 95, 99.7. So if this right here in the middle is my mean, right? Here is 1 standard deviation. This green right here represents 68%. If I take a different color here, if I go out another standard deviation, right? Let me actually write this here. This is -1, +1. This is over here, -2, plus 2 right within the blue that I'm illustrating here, you have 95%. And then if I go out one more, we'll do this in pink. We'll go all the way to here. This is minus 3, plus 3, right within this pink region, which I know I'm writing over colors here, is 99.7% of your data. So you'll notice being more or less than 3 standard deviations from the mean is extremely unlikely, right? You only have a 0.3%, 3 out of 1,000, to be greater than or equal to 3 standard deviations from the mean, right? So it's actually interesting when you think about SAT scores, the average on each section is normed to be 500, and it has a standard deviation of 100. Plus or minus 3 standard deviations means 200 to 800, which is the exact score range that you can get. So, there is one last concept that I want to talk about today with you guys, and that is, how do I calculate how far away I am from the mean, right? Like, this rule is great, but what if I'm 1.5 standard deviations, right? And how do I know that? So what comes in with that, and why it's called a z-table, is we have something called a z-score. Now, it looks kind of funky. It looks like x minus mu over sigma. Right? Now, a couple of important pieces here. Sigma, obviously that's my standard deviation. Mu is the mean of your distribution. And x is the value. Right? So all a z-score does is tell you how many standard deviations you are from the mean. Right? And then how is that useful? So, for a quick example here, let's say I have a distribution where the mean is, we'll use SATs for example, right? The mean is 500, the standard deviation is 100. Now I know this would be very easy to calculate, but let's just say, for the sake of this problem, let's say you're super smart, right? On the math section of the SAT, you got a 720, right? So to compute my z-score using all of that, well, I know it's value minus mean over standard deviation. So when I plug in, it's 720 minus 500 over 100, which we all, we're all smart. We can do this math here. We get 2.2. So, meaning my score is 2.2 standard deviations from the mean, right? Now, interestingly, if I go to my z-table and I find 2.2, right, I get this number of 0.9893. What does that correlate to? Let me change my font color here. So, remember I said the area underneath is the probability, right? So this means there is a 99, if I round it here, % chance that you did better. Or, in other words, you did better than 99% of people, right? There's a 99% chance that someone got a score lower than your score. That sound familiar? Because this is how you get your percentile rank on the SAT. They use the normal distribution, so that means this is the 99th percentile. Or maybe they told you were in the 98th percentile. But z-scores are really, really helpful because they tell you what's the probability that something is less than or equal to your given data value, right? So they're helpful because they tell you, I'm going to write this down now, the probability that there's a value less than or equal to your z-score value. So we can figure out, hey, what's the probability that this, particular, in terms of like a real world context, is something defective or not? What is the probability that something breaks as many times as this thing breaks? So I don't want to make this video too long, so that's where I'm going to end it. I hope you guys have a wonderful weekend. We'll talk more about it on Wednesday next week. And just to give you a heads up, you guys are going to have your first mini quiz on Wednesday. It's just going to cover histograms and box plots. We will talk more about it as the week goes on. I will post some review stuff for you. So, again, guys, have a wonderful weekend. Actually, I shouldn't say, not Wednesday. Wednesday, we don't have the remote day. So, it'll be Thursday or Friday, depending on when I see you. So, again, for the third time, have a wonderful weekend, and I will see you all next week. Bye, guys.